Now we're going to take a little more detailed look at the process described in the preceding clips. Let's look more closely at the equation y double prime minus y equals t squared. Now, I chose y prime minus y just because it's very simple, has a very simple solution, but this could be any second order equation. Matter of fact, we can do this for higher order equations, but this could be any second order equation for which we can find a solution, for which we can find the solution to the homogeneous equation. So the homogeneous equation is y double prime minus y equals 0, and we're going to call this the homogeneous equation. So let's go ahead and make a little note that that's the homogeneous equation that goes with this non-homogeneous equation. And this is called the characteristic equation. I didn't write that very clearly, but you understand what I'm saying. This is a characteristic equation for this homogeneous equation. Just a little bit of terminology. Now it's real simple to find the solutions to this equation. We have a solution set, actually a fundamental set. The t here isn't real clear, so maybe I can enhance that a little bit. General solution to this equation then is y equals c1 e to the t plus c2 e to the negative t. I'm going to make the statement, if g of t is a solution of this equation, that is our non-homogeneous equation, then if I add the solution to the homogeneous equation, that is what we call the solution to the characteristic equation, we're going to call that the characteristic solution. If we take this characteristic solution here and add it to our g of t here, it's also a solution. Now why is that? You might have worked through the details of that in response to the preceding clip, but the reason for that is fairly simple. Y double prime is going to equal, well, the second derivative of this, c1 e to the t is just c1 e to the t. The second derivative of c2 e to the t is c2 e to the negative t is c2 e to the negative t, so that the second derivative of this part of the function is this, and the second derivative of g of t is just, well, g double prime of t. Now if we plug that into the equation, into the left-hand side, y double prime minus y is then going to equal this plus this. Right there's your y double prime minus all of this, which is your y function. If we do that subtraction, the c1 e to the t is going to, well, the c1 e to the t is going to match up with a negative c1 e to the t to give you 0. c2 e to the negative t is going to match up with a negative of c2 e to the negative t, and we're just going to end up with g double prime minus g. So that the characteristic solution, the solution to the homogeneous equation, does just what it does. The solution to the homogeneous equation is the function, the general function, that makes this 0, because the homogeneous equation is this equal to 0. So that this term and this term have to cancel out, leaving us the g double prime minus g. But then g is a solution to our non-homogeneous equation, to our original equation. By hypothesis, we said if g is a solution of this equation, well, if g is a solution of this equation, then that means that g double prime minus g has to equal t squared. So since g of t is a solution of this equation, y double prime minus y has to equal g double prime minus g, which is equal to t squared. Again, then, if g of t is a solution to this equation, any solution to this equation, adding the solution to the characteristic equation, the solution to this homogeneous equation, still gives us a solution. Now we can say more. Okay, we can say that any solution of this original equation has to be of this form, the form of the solution we just looked at, where g of t is a solution of this equation. I'm going to let you work through the details of why that's so, but I will repeat a statement I made earlier that any two particular solutions differ by solution to the homogeneous equation. And this is just a consequence of the linearity of the original equation, and it's actually very easy to prove this. In terms of what we have seen, we can say this then. Y double prime minus y equals 0 is a homogeneous equation, has a solution c1 to the t plus c2 to the negative t. We call that the characteristic solution, and we call this the characteristic equation. I haven't written that down. Y double prime minus y equals t squared is a non-homogeneous equation. We don't have a 0 on this side. And any solution of the form g of t we call a particular solution to the non-homogeneous equation. Any solution of this equation is then a particular solution to the non-homogeneous equation. And we can make the really important statement. Every solution of this equation is of the form y of t equals yc of t plus yp of t, where yc of t is the solution to the characteristic equation and yp of t is a solution to the non-homogeneous equation, a particular solution to our original equation. So our yc of t is just this. This is our yc of t right here. And our yp of t is our solution that we call g of t for right now. Okay. Particular solution is any solution to the original equation. And since every solution can be written this way, we call this the general solution of the non-homogeneous equation. And it will apply for any particular solution y sub p. Doesn't matter what the particular solution is. Again, two particular solutions are going to differ only by a solution to the characteristic equation, so that this statement is going to hold. Having developed the terminology, we'll go on in the next clip, in the next couple of clips, to look at various ways we can reason out the particular solution. We have not yet found a particular solution to this equation. All we've done is asserted some properties of the particular solution. And we'll find that for certain types of functions on the right-hand side here, we can use common sense to reason out the form of our particular solution, and then we can do a little bit of manipulation and arrive at a particular solution.